Cyclotron. One of the most interesting applications of motion of charged particles in electric and magnetic fields is the cyclotron. It is a machine used to accelerate charged particles. E. O. Lawrence and M. S. Livingston invented this machine in 1934. Let us first try to understand what a cyclotron is made up of on a fundamental level. Well, to start with, we have an electromagnet which continuously generates a magnetic field as shown here. Here, the magnetic field goes from the bottom to the top. Inside this magnetic field, we have two metallic plates, D1 and D2. They are also called Ds, as they are in the shape of the letter D. Both these magnetic fields are connected to an alternating electric source, which changes the polarity of the electric field periodically. Now imagine a charged particle P. A proton, for example, is at the center of this cyclotron. This proton will be attracted towards the negative plate, D2. As it enters the plate, it is acted upon by the magnetic field, and we know that a charge moving with a velocity v perpendicular to the magnetic field B will move in a circular fashion. As soon as this proton exits the plate and enters the gap, the polarity of the plates changes, and D1 becomes negatively charged. Hence, P will now get attracted towards D1 and will accelerate towards it. This increases the energy of the particle P. As it enters D1, due to the magnetic field, it will start moving along a circular path. But this time, as it got accelerated while entering, the radius of the circular path will be more. Again, as it exits D1, the polarity gets reversed, and now D2 gets negatively charged. Hence, P will now get attracted towards D2 and will accelerate towards it. This increases the energy of the particle P further. As it enters D2 due to the magnetic field, it will start moving along a circular path. But this time, as it got accelerated while entering, the radius of the circular path will be more. This cycle continues and the particle P keeps on moving spirally. To maintain this spiral movement, the polarities of the Ds has to be reversed in a time interval t by 2. Where t is the period of revolution of the particle. T equals 1 by Vc, which equals 2 pi m divided by q times b, or Vc equals q times b divided by 2 pi m. This frequency Vc is also called cyclotron frequency. If we denote the applied voltage as Va, then the requirement is Va equals Vc. This condition is called the resonance condition. Once the particles are accelerated to the required speed, they are then deflected using a magnetic field. They then leave the system via an exit slit. This accelerated particle can then be used for bombarding other atoms, molecules or solids according to the requirement. We know that V equals Q into B into R by M. Here, R is the radius of trajectory of the particle at exit. This radius is equal to that of the D as well. The kinetic energy of the particle is half mv square, which equals Q squared into B squared into R square, divided by twice the mass. The important fact here is that the time for one revolution of the charged particle is independent of its speed or its radius of orbit. This was a schematic of a cyclotron. In reality, it appears as shown here.